Hello everybody. Today we will be talking about property testing. It is an important and interesting computational framework that has been developed in the last 15 years. There have been some attempts at it even earlier than that, but in the last 10 to 15 years this particular model of computation has become quite popular, and we will be exploring this model of computation in the context of two examples. But before we get into those examples, let us first motivate the computational model. One scenario that motivates property testing is as follows. We often have data stored in a cloud far away from the actual computer that performs computation. So this is one scenario that clearly motivates property testing. We have data. It could be a graph, it could be a large data set, it could be some complex function. This data is somehow stored in a cloud or a data center that is physically far away from the computer that actually performs the local computation, and this local computer has some question that needs to be answered about the data. Unfortunately, the only access to the data is through a very slow network, and therefore any information about the data has to be accessed via queries through the network. And these queries travel from the computer that is interested in answering the question to the data center, and then the data center has to process the query and send back a response. In this context, the local computation performed in the local computer is much faster than the speed at which the queries are answered. So we will therefore need to design a computational model that in some sense ignores local computation and is very careful about the number of queries that are sent to the data center and received from the data center. So under this motivation, we will first provide a formal computational model and explain all the parameters that govern this computational model, and present an overview of a couple of examples. That will be the first segment of our lecture. In the second and third segments, we will consider two examples. One would be the example of testing connectivity in a graph, and the other will be the example of testing whether a particular Boolean function is linear or not. And of course, we will define all the terms more carefully when we look at these examples. For now, let us look at the property testing framework and build an understanding of what the property testing model is. At the core of the model is a Boolean question that we need to answer about the data, and recall that the Boolean question has to be answered in a local computer, whereas the data is stored in a faraway data center or a cloud or whatever you will. And typically the Boolean question we ask is of the form, does the data have some property, and let's call that property P. An example of such a property would be to ask whether a network graph, which is the data, is connected, which is the property. So if the graph is connected, then we are happy, and if the graph is not connected, obviously we are a bit unhappy. We typically would want, if our data represents a network graph, we typically would want that network graph to be connected. So, and we would therefore be interested in knowing whether the graph is connected or not. And that's the Boolean function that we are interested in. And with while trying to answer this Boolean question, we must minimize the number of queries. Too many queries would slow down the entire process because queries have to travel through a very slow network. And for this purpose, we will simply ignore the local computation because it's much faster, and only concern ourselves with the number of queries. And in particular, in the property testing framework, we are interested in in trying to answer the Boolean question with very few queries. In particular, we want to answer the Boolean question using only queries that are sublinear in n. For example, a constant number of queries, or the number of queries being logarithmic in n, or the number of queries being square root of n, or some such sublinear quantity in n. Of course, this would mean that we don't even have enough number of queries to read the entire data set. Clearly, the data is in the cloud because it is large and does not fit within the local computer. So allowing the local computer to read the entire data set before answering the question would defeat the purpose. So that is the crucial reason why we insist on the number of queries being sublinear in n. Clearly you would be wondering, how can we answer any meaningful question about the data set in time, or the number of queries here, that is sublinear in n. Clearly, this sublinearity requirement will demand a compromise. So we will not be able to answer the question with 100% accuracy. We will have to answer the question in an approximate fashion. And here's how we will model this part of the requirement. If the data has the property P, so for example, if the graph that we are concerned with is connected, for example, then we will accept the data set. And here accept means we accept that the data has the property P with probability at least 2/3. On the other hand, if the data does not have the property P, we need to be a bit more careful. If the data can be slightly modified to acquire the property P, then it is going to be computationally difficult to identify the fact that this data set does not have the property P because the data set is very close to having the property P. And therefore, in order to be able to design good algorithms, we simply ignore these situations. And they also make sense from practice because typically we are willing to live with a little bit of compromise on the accuracy. And if the data set is close to having the property P, we will be willing to compromise and say we don't care if the question is answered correctly or not. However, if the data requires a lot of modification before it can acquire the property P, so then this implies that the data is far from having the property P. And in this context, we require that our algorithm should reject the data set, meaning that our algorithm should be able to identify that the data set does not conform to property P, does not satisfy property P, and therefore we should be able to reject it with probability at least 2/3. And of course, we will need to do this with as few queries as possible. So let us think a little bit more carefully about this compromise, and let's try to formalize this. And towards that, let's first start with some motivation. And let's think of the context where you are working for an online social network company, and your network, social network, is stored in some cloud, and your boss is concerned about whether the social network is too fragmented or not. If it is perfectly connected, great. If there is some small fragmentation here and there, that is also fine. But obviously, you and your boss will have to be concerned if the social network is has a lot of fragments, and so your boss asks you, to try and see whether the data is too fragmented, and you ask, okay, so what would constitute too much fragmentation? And so then let's say you converse with your boss and you come to the conclusion that many edges must be added to attain connectivity. And if that is the case, then the graph is said to be too fragmented. If you can connect the graph by just adding a few edges, then you don't quite call it too fragmented. So let's formalize this a little bit more carefully. Let's say you and your boss come to the agreement that if there are m edges and the only way to connect the graph is by adding more than say a small fraction 0.001 times m number of edges, then you would say that the graph is too fragmented. If on the other hand you can get the graph to be connected by just adding fewer than 0.001 times m number of edges, then you don't care. You are willing to live with that amount of fragmentation. And such a motivation leads us to the definition of the notion of being epsilon far from having property P. So let's formally define that. A data set is said to be epsilon far from having property P if more than an epsilon fraction of the data must be modified, and this could include some additions, deletions, edits, so on and so forth, modifications for the data to acquire the property P. So if the data already has P, then you don't require any modification at all. If the data set is close to satisfying the property P, then with just a small number of modifications you should be able to change the data set into having the property P. But if it's epsilon far from having the property P, then you will need to make a lot of changes. At more than an epsilon fraction of the data must be modified, and this is the notion that we use to define epsilon far from having property P. And notice that just to be clear, this is purely a definition of what we mean by the data being far from having property P. Algorithmically, we would not be concerned about making these modifications to check whether the data set is far from having property P or not. Typically, we want our property testing algorithms to answer the queries without actually modifying the data set, just by querying and getting to know the data set. However, this notion of being epsilon far from having property P will be exploited in analyzing our algorithm. So now that we know, we have defined the notion of being epsilon far from having a property P, let's rephrase the framework, the property testing framework a little bit more formally. If the data has property P, then we would like our property testing algorithm to accept with probability at least 2/3. Otherwise, if the data is epsilon far from having the property P, then we would want our algorithm to reject with probability at least 2/3. Otherwise, we don't care. And of course, all this has to be done with as few queries as possible. So let us briefly look at the two examples that we will be considering in the next two segments of our lecture. The first property that we will be concerned with is testing whether a given graph is connected or not. So the cloud has a large graph. Let's say it's stored in the form of an adjacency list, and locally we have the question, is the graph connected or not? And we can send out queries of the form, select a random node, what are the number of neighbors that that node has, and then what's the fifth neighbor of that node, and so on and so forth. So we're allowed queries of that form, and we will receive appropriate responses. And with as few queries, we need to answer the question whether the graph has a particular, as the connectivity property or not. The second property testing example that we will consider is testing the linearity of a Boolean function f. The Boolean function f will be stored in a cloud, and the local computer has access to the function via queries, and the queries are of the form, what is the value of f of x for some given x? And using the responses, we will have to answer the question of whether f is linear. And of course, we will formally define linearity of Boolean functions in the third segment when we discuss this topic. And so that brings us to the end of the first segment. In the second and third segments, we will look at these two examples in greater detail. Thank you.